All right, so as promised, this is going to be the applications of the cross product. I'm going to start by sharing the notes with you. So here we go. All right, so for our first example, we're going to find a unit vector orthogonal to the two vectors A and B given here. I'm sure you memorized the example from last time, but these are the vectors that we've already found the cross product of. And so the good news about that is that we already have an orthogonal vector, right? So I should probably give it a name. Let's call it C. Let's let C equal the cross product of A with B, which is -1 for -1. So this vector is orthogonal to both A and B. All we have to do then is normalize it. So if you'll recall how we normalize a vector is we divide the vector or multiply the vector by 1 over its magnitude. So step 1 is to find the magnitude. So the magnitude of C is going to be the square root of -1 squared plus 4 squared plus -1 squared. And when we do that computation, we get square root of 18, which is 3 root 2. All right, so then a unit vector, not sure one could actually recognize that word as unit. Let me write it a little bit nicer. Unit vector orthogonal to both A and B is, drum roll please, we're going to take 1 over the magnitude of C times C, which is 1 over 3 root 2 times -1, the vector -1 for -1. So that's -1 over 3 root 2, 4 over 3 root 2, -1 over 3 root 2. But we certainly don't want to leave it that way. We want to rationalize. We don't like those roots in the denominator, so I get negative square root of 2 over 6, 2 square root of 2 over 3, negative square root of 2 over 6, and that is our answer. Yay! Okay, now you might have said, come on, professor, that's not a really great application. All right, but geometric application, we can use the cross product to find the area of a parallelogram. All right, how about this? If we locate vectors u and v as adjacent sides of a parallelogram as shown in the picture here, which is figure 2.57 from the textbook, to be fair, then the area of the parallelogram is going to be the magnitude of the cross product of u with v. So let's see why that's going to be true. Well, we know the area of a parallelogram is the base times the height. The base is given by the length or magnitude of the vector u, and the height is, you can see we have a right triangle here with hypotenuse given by vector v. So the height is going to be the magnitude of v times sine of theta. And so, put it all together, the area is going to be the magnitude of u times the magnitude of v times sine theta, which we recognize as the cross product of u with v, well, the magnitude of the cross product. See, told you it was true. Now also, since a triangle is half the area of a parallelogram, we can also use this theorem to find the area of a triangle with adjacent sides u and v, right? How do we do that? Well, we just take half the area of the parallelogram, so we get 1/2 times the magnitude of the cross product of u with v. So let's do an example of this. Let's find the area of parallelogram ABCD with adjacent sides, vectors AB and BC, and the 3 points are given there. All right, so we'll let U be equal to the vector AB. That's very simply going to be, let's see, 0, the entries are 0 minus 2, 1 minus negative 3, and 2 minus 4. So it's the vector with components negative 2, 4, and negative 2. And V is going to be vector BC, which is going to have components negative 1 minus 0. That looks more like I was doing some kind of stick figure. Negative 1 minus 0, as I was saying, 2 minus 1, 0 minus 2, which is negative 1, 1, negative 2. So now we're going to find the cross product of those two vectors. And then we will find its magnitude, because you can't find the magnitude without the vectors. I challenge you to try. Okay, so the first row is as usual, the unit vector is ijk, and then the entries in the second row come from U, they're negative 2, 4, negative 2, and the entries in the third row come from V, they're negative 1, 1, negative 2. Like we always do, we are going to use a cofactor expansion on the first row. So let's do it. All right, so we have the determinant, our first matrix has first row 4, negative 2, second row 1, negative 2, minus, so our second matrix is going to have entries, let's see, so that is going to give us in the first row negative 2, negative 2, and in the second row negative 1, negative 2. And finally, we're going to get negative 2, 4, negative 1, 1 as the rows of our third matrix. And let's do the computation. So I have the quantity 4 times 2 minus 1 times negative 2 times I minus the quantity negative 2 times negative 2 minus negative 1 times negative 2, that's times j, plus negative 2 times 1 minus negative 1 times 4 times the unit vector k. So that's negative 6i plus 2j plus 2k. All that's left is to find the magnitude of that. All right, so the area is going to be the magnitude of that cross product, which is the square root of the quantities negative 6 quantity squared plus 2 squared plus 2 squared. That gives us the square root of 44 or 2 root 11. Awesome. Practical applications of the cross product include the calculation of torque. And you can see the textbook for some more details, or if you're doing some kind of mechanical engineering or an engineering where you're going to discuss torque, civil maybe, then you'll also see it there. But that kind of makes sense, right? Because torque involves a twisting. And what are we doing when we're finding the cross product using the right-hand rule, right? We're curling our fingers, we're kind of twisting. Now there's one more application of, well, technically it's an application of with the dot product and scalar product sort of working together to define something called the triple product, or the triple scalar product, I should say. And that triple scalar product of 3 vectors u, v, and w is the dot product of u with the cross product of v and w. And we can use determinants to find the triple product as opposed to finding the cross product and then taking the dot product. So if we have 3 vectors u, v, and w with their components as given, the triple scalar product is found by a 3 by 3 determinant, and each row represents one of the vectors and in order. So the first row is going to be u, components. The second row is going to be the components of V, and the third row is going to be the components of W. We do not want to make a memorization. You don't want to memorize that, what that expands to, right? Just enough, it's enough to remember the actual matrix. And the scalar product has a geometric interpretation as well, and that's the volume of a parallelepiped. So a parallelepiped, say that 10 times fast, is kind of like a box, but it's a box that's kind of at an angle, if you don't remember from geometry. And if I have a parallelepiped with adjacent edges given by the vectors u, v, and w, the volume is found by taking the absolute value of that triple scalar product. Isn't that cool? Now, even cooler, we can use the triple scalar product or that actual volume to show that three vectors are coplanar. Now you might go, volume coplanar, huh? So let me explain. If the volume of the parallelepiped is 0, that means that one of the dimensions had to have been 0. One of the vectors had to have been 0. Not one of the vectors had to have been 0. It means one of the dimensions of the parallelepiped had to have been 0, right? Either the height, for example. And so if the height is 0, then that means that all of the vectors are in the same plane, because how do we get the height? We get the height from the vectors. Anyway, so take a peek at the textbook for some examples of this. And as usual, I have some lovely suggested exercises for you. Next time, we're going to talk about equations of lines. So hope everyone has a great day, and I'll see you next time. And